Hi everyone. It's our second lecture for class 11. In our last lecture, we have discussed regarding the general state electronic configuration of carbon. And that was as per 3D concept, that is 1s2, 2s2, 2p2, right? Now, now we need to draw a diagram. It's a diagram to show, that is, the energy level of 1s 2s 2p along with its energy. Energy is basically, we are trying to graph energy in y-axis, and in x-axis here it is 1s, it's 2s, and this one is 2p, right? Now, in ground state electronic configuration, 1s orbital containing 2 electrons. In 2 electrons, first electron will occupy here 1s orbital in a clockwise direction. Another one will then pair up in a anti-clockwise direction. Or first one is a anti-clockwise direction and second one is in a clockwise direction. Then next orbital is 2s. In the same way, 2s first one of a electron will assign here, then it will pair up. And for 2p orbital, as per Hund's rule, the first electron will here and the second electron will occupy at here. So this configuration is the ground state electronic configuration of carbon. Now when carbon is heated, it moves to excited state, and this excited state having electronic configuration is different. How is it? Let's see. In the same way, we have to draw first 1s orbital, 2s orbital, this one is 2p orbital, right? Well, and this one is the energy. When carbon is heated, it goes to the excited state. It goes to the excited state. And in excited state, one of a electron from the 2s orbital moves to 2p orbital. Then the electronic configuration becomes 1 2 1 1 1 1. Actually, this electron moves to here, to pz. Now you have single electron in a 2s orbital and single electron in all 2p orbital, right? The electronic configuration is 1s2, 2s1, 2p3. Now here is few things we need to know. Actually, this energy is a 1s energy, right? And this one is a 2s energy. This one is a 1s energy and this one is 2s energy. And this one is a 2p energy, right? I can write here 1s, 2s and 2p. 1s, 2s and 2p. The energy difference in between 1s and 2s it's huge. That is 1s, 2s is much more compared to energy difference in between 2s, 2p. Since 2s and 2p energy are comparable, then that's the reason electron moves from 2s orbital to 2pz orbital, right? Not from 1s orbital to 2p orbital. And that's the reason of electronic configuration of carbon is 1s2, 2s1, 2p3. Now, these 1s2, 2s1 and 2p3 have four unpaired electrons. Four unpaired electrons in orbital. So the valency is 4. That's the reason carbon having tetravalency, right? Next. Just a second, I need to do something here. Next we need to know tetravalency, covalency, ground state, electronic state, everything done, right? Now here is we need to know something, that is the concept of hybridization. Concept of hybridization. What is hybridization? Mixing of atomic orbital. Mixing of atomic orbital. Right? See, in excited state, we have four unpaired electrons in a 2s and 2p orbital. Now, here is a scope to mix 2s orbital. Okay, right, I'm trying to write here. Wait, it's 1s, it's 2s, and this one is 2p. Right, 2p, x, y, and z. Okay, here it is 2, well, 1, 1, 1, 1. Now, in this scenario, we have seen that is hybridization happens by mixing of atomic orbital. Hybridization is a phenomena. When 2s orbital are mixes with 2p orbital, there is a scope of mixing of four hybrid, there is a scope of forming four hybrid orbital, and that hybrid orbital is known as sp3 hybrid orbital. Okay, I am not including 1s orbital here, only the mixing is happening here, 2s and 2p. So four unpaired orbital are mixes here and forms sp3 hybridization. Why it is sp3? Because one number of 2s with 3 number of 2p. That's the reason sp3 hybrid orbital. And this hybridization we will see in a methane molecule that I will try to discuss later. Now, In a second option, here is a possibility of mixing of two atomic orbitals. One is 2s mixed with 2s mixes with 2p, just like this one, and 2pz remains intact. Pz I can write here, right? 1 1 1, and here is a clockwise anti-clockwise both. Now here is a possibility of mixing 1 2s with 2p orbital, and that hybridization is known as sp2 hybridization. Just a second, right? And this hybridization we will see in a CC double bond, that is 2C2H4 molecule. And number third option is sp hybridization, where 1s is here, 2s is here, and 2p, py and pz remains separate, px, right? 2p right here, 2px, 2py, and 2pz. It will be better for, right? So here is a possibility of 1 2s with 1 2p, that is px, sorry, sp. So this hybridization is known as sp hybridization, which we will try to explain in a C2H2 molecule. Now one thing I need to say here, that is, when S is mixing with p orbital, completely new orbitals are formed. That one is a hybrid orbital, and their energy are completely new, not identical with previous S and previous P. So it's a new hybrid orbital having new energy, right? Okay, great. So this one is hybridization concept. Next, we try to okay, next, where it is, try to save the data first. Just a second. Wait. Okay. Next one is we need to discuss. Okay, first we'll see the three molecules, that is methane, ethylene, and methane, ethene, and ethyne. In methane, carbon having tetravalency. That means carbon has hybridized sp3, right? This one. Here is a carbon, sp3 hybridization. Here single electron, single electron, single electron, single electron. Now this carbon having 4 electrons in outermost orbital. Now to make it octet, at least carbon needs another 4 electron, and that 4 electron will come from hydrogen by mutual sharing of electrons, and that's the reason methane molecules are formed right here. So we can write here H, again one other H, again another H, again another H with, and what about this one? Just a sec, where is that color? Font color. Okay, so this one. So this hydrogen will give another molecule here, another electron, this one another electron, this one, this one. So in this way, methane molecule has been formed. Now, by default, since four hydrogen atoms are surrounded here and carbon is in a center, that is, we can say that is they have a 90-degree angle difference in between hydrogen, carbon and hydrogen bond. But actually the bond angle in between hydrogen, carbon and hydrogen is more than 90 degree, that is almost 109 degree 28 minutes, which proves that here the hybrid orbitals are formed by the hybridization of the carbon, right? Here is a hint. Actually, this one, this one, this one, this one, this one, tetrahedral shape, and this angle is known as 109 degree 28 minutes, and this structure of the methane is known as tetrahedral structure. Right. Our next example is C2H4. It is known as ethene, or we can write C double bonded. Actually, structure is this one. By the way, in methane molecule, the carbon versus hydrogen having bond nature sp3 versus s, or we can say hydrogen versus carbon is s versus sp3, right? The next molecule is C2H4. In C2H4, we see that is carbon is double bonded with another carbon, and this carbon also containing two hydrogen atoms. Suppose we are trying to identify this carbon is a black carbon and this one is a red carbon. It will be easier for us to understand the situation, right? So first, here is a carbon, red carbon, and this red carbon having same electronic configuration in an excited state, we can write here in this way. It's a 1s, it's a it's a sp hybridized, sorry, we can write here in this way, this one, yeah, it's a pz, and these are sp2 hybridized, this one, this one, this one, all are three sp3 hybridized, and the electrons are this one, this one, this one, this one, and here is a double, right? Okay. Now, this black carbon atom, we can write here, and this black carbon atom also having the same electronic configuration, that is pz, sp2, 3 sp2, that means this one, this one, this one, and also 1s, right? Now this one is a C, black C carbon atom, and this one is a red C carbon atom, just like in a picture. C, that is black C carbon atom, is has made a coordinate bond with two hydrogen atoms. We can write here by different color here. One of a hydrogen is here, it's just opposite direction. Again another hydrogen also in a opposite direction. Here's this H, that is yellow color, and this one is a pink color. We can write here, sorry, once again, pink color, this one pink, this one pink, and that pink color hydrogen has bonded made a coordinate bond with red carbon. So we can write here this way, that is one of a H is opposite direction, one of each having opposite direction. Now from these two images, it's clear that is carbon has made a sigma bond with this hydrogen and this hydrogen, which is from here, and this carbon also having made already has made two sigma bond with these two hydrogen. Now these carbon carbon double bond, in this carbon carbon double bond, one bond is sigma bond, another bond is a pi bond. Now this sigma bond is formed in between black carbon and red carbon. Actually this one made a coordinate bond with black carbon and red carbon. So the picture becomes this one, that is C single bond, H H, red color, H H, right? All are sigma bond. And PZ here, they have not yet paired up. So it's a PZ orbital. Here is also another PZ orbital of red carbon. Both are containing 1 electrons. When these lobes comes closer, there is a possibility of making a again another covalent bond, which is formed by the partial overlapping of the orbital. In this way, ethene or ethylene compound is formed. So in ethylene, in between carbon carbon double bond, one bond is sigma, another bond is pi, and the bond nature, carbon hydrogen bond nature, carbon versus hydrogen bond nature are sp2 versus s, carbon 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 versus carbon bond nature, sp2 versus sp2, and and what about, yeah, and pi bond is carbon versus carbon, that is pz versus pz. This one is a pi bond and these are all sigma bond, right? Let's our last example is sp hybridization. Sp hybridization we see in a ethine molecule having formula C2H2. Very good. In C2H2, the molecule carbon carbon having triple bond property, and in this triple bond two bonds are pi bond, only one bond is sigma bond in between carbon carbon, right? Now we need to see how they have formed. This carbon, left side carbon is black carbon and right side carbon is red carbon, right? Red carbon. Red carbon also having hybridization, that is sp hybridization, right? Sp, and py, pz are alone, and the black carbon atom also having sp hybridized. So we can write here py and pz, right? Now single electron, single electron, single electron, single electron, single electron, single electron, single, single. These are sp and these are py. You can write here, pz you can write here. You can write here sp, it's py, it's pz, right? From here, there is carbon out having tetravalency, and out of 4 valency, one of a bond is formed with one hydrogen. So here is a one hydrogen which is giving, here is one hydrogen which is giving the another electron in a different direction, right? In the same way, here is another hydrogen which is also, this hydrogen is also giving in a different direction, right? And this sp electron is making a covalent bond with this sp. So what we have seen, there is carbon here, black carbon, red carbon here, black carbon, one of our, okay, try to write in blue pen, one of our bond is formed, it's a black bond, okay, it's a black bond, and this carbon also has made again one hydrogen here and one hydrogen, right? One hydrogen. Now this py orbital is here, upper lobe, lower lobe is another one, this one A. Same way, it's a py, it's a py, it's a upper lobe, it's a lower lobe, right? Now try blue. This electron, it's a py, right? Py, and this one is py, right? Py, and pz, where it is, well, it's a pz, and this one is a pz, so we can write pz, pz, right? Now from here, when these two lobes are comes closure and there is a possibility of partial overlap, then there is a formation of pi bond. So pi bond is formed here with this one and this one. So in ethine, we can say this carbon hydrogen having sp versus carbon and hydrogen, sp versus s bond nature. Carbon with carbon is sp versus sp, right? And py 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 pz pz, all are pi bonds, right? These are the total example of the three hybridization in our syllabus, right? I hope that is it will clear the entire concept of hybridization. Okay, that's all for today.